Hello everyone, I am Dr. Naresh Kumar, Assistant Professor from the Department of Electrical and Electronics Engineering, Institute of Aeronautical Engineering, Hyderabad. Today we are going to have a discussion on power MOSFET. First, I will explain the basics of power MOSFET, the symbol of power MOSFET, and next the difference between power MOSFET and power BJT. Already we discussed power BJT, so the difference between power MOSFET and power BJT, and next structure of power MOSFET. After that, the working of power MOSFET, transfer characteristics and output characteristics of power MOSFET, and next switching characteristics. Power MOSFET can be used as a switch, so that switch on, turn on and turn off characteristics we will discuss. Next, advantages and disadvantages. After that, finally applications of power MOSFET. So now here if you see the basics of power MOSFET, what do you mean by power MOSFET? The full name for power MOSFET is metal oxide semiconductor field effect transistor. So power MOSFET. And next it is a 3-terminal device. Here in this we have total. So this is gate, drain, and next source, 3 terminals, and here it is a voltage control device. In the previous power BJT, that is current control device, the output voltage and output current is depending on base current only, depends on only current, that is current control device. But here this voltage is depending on this output voltage and output current, VGS and VDS are depending on gate voltage, gate source voltage only. Due to that reason, it is also called as a voltage control device that we will see in the detail, and it is a unipolar device. So BJT is a bipolar device and power MOSFET is a unipolar device. In the BJT current conduction due to the electrons and holes, but here in the power MOSFET the current conduction is because of only electrons only, and it is a majority carrier device. So its conduction, majority carrier device, conduction due to the electrons only. And next, its input impedance is very high. This is one best feature from the input side. And next, if input impedance is very low, means current is low. So low input current, high input impedance. And next, it is a non-linear device. Voltage current characteristics for this power MOSFET are non-linear characteristics, not a straight line, not passing through the origin. Due to that reason, this power MOSFET is known as a non-linear device, and it is a fully controlled device. Turning on and turning off is in our hand. So here it does not require any external circuit. Commutating circuit is required to turn on and turn off. So turn on and turn off is in our hand. It is an active device. And next, it's in the BJT. BJT is a negative temperature coefficient for the resistance, but here power MOSFET having positive temperature coefficient for the resistance. And next, basics here. It is free from the secondary breakdown, but in case of power BJT, in the power BJT secondary breakdown occurs, but here there is no secondary breakdown voltage. And next, its safe operating area will be in first and fourth quadrant. And next, it can be used for high speed applications and high frequency applications, because its turn off time is very quick, so is very low, short turn off time. So because of that reason, short turn off time means frequency is high, and frequency high means high speed, we can turn off easily. So that is the reason so it can be used in high speed and high frequency application and low power applications. So now here there may be in between drain and source there may be a resistance, large resistance, due to that reason large power dissipation occurs. So because of that reason it is used in the low power applications. So these are the basics. So these things you need to remind. So this I will explain in the working characteristics, in the structure, everything I will explain in detail. So now here if you see the symbol of power BJT. So a symbol of power BJT, it looks like this. So first it is having drain. This is drain and this one is a source and this one is a gate. So now this is the N channel power MOSFET and this is the P channel power MOSFET. Here arrow is the orientation away from the source and here orientation towards the source. Drain, source, gate. It is having three terminal. In the basics I have given one statement. So power MOSFET is a three terminal device. The terminals are drain, source and gate. So the real picture of power MOSFET, it looks like this. And next construction of power MOSFET. So this figure is only for low power. So throughout the analysis we will discuss only N-channel MOSFET only. So N-channel enhancement power MOSFET only we will discuss. So now here this is low power applications power MOSFET I am explaining. So now here it is having drain, source and gate, three terminals. So here in the P substrate, two N plus substrates are diffused into the P substrate and two N plus layers are diffused into the P substrate. And here this is SiO2 layer, this one is a SiO2 layer and these are the series one, this is metals. So these are the metals and this one is a SiO2 layer and this is the ohmic contact. So this is the construction. So now here what will happen in this, first if you give the this is some voltage to, this is body, some voltage to this one. So gate is positive with respect to body. So now here there may be, so this SiO2 layer acts as a capacitor. So there may be a channel, one channel will be induced. If you give some amount of VGG and there may be a channel will be generated. So now here some amount of carriers field effect, electric field will be developed. There may be a channel will be developed. So now here, so this channel. So now here when you apply drain to source and then current flows from this channel from drain to source. This is the current direction. So now here this is metal oxide semiconductor. Why it is named as a metal oxide semiconductor? This is metal and this is oxide and this one is the semiconductor, metal oxide semiconductor field effect transistor. So now here if you see this one for high power applications, N-channel enhancement power MOSFET. So now here it is power MOSFET here. So for low, previous one, there what is the main drawback is there is a, from the drain to the source, the large amount of resistance, because of that large amount of heat dissipation. So that can be used only for low power applications. But this this is used for high power applications. In this, the parallel connection of thousands of basic MOSFET cells on the same chip of the silicon. So here this is one MOSFET and another MOSFET. This is also N minus. Now here two MOSFETs parallel connection. So now here in this the three-dimensional picture, if you see this one, so here a source, two sources and gate and drain. So now here 1000, so this is 1 and 2 3 4 5 6 and 1000 number of basic MOSFET cells on the same silicon chip. So now here we have only two I'm explaining. So now here this is a gate. So here is the gate, and next this is the n minus layer, and this is n plus layer, this is p layer, and next this is n minus layer, and then next this is n plus layer. So here first let us see the construction. This is n minus layer, n plus layer is connected to the drain, and next n minus layer is epitaxially grown on n plus layer. After that, this p plus layer is diffused into the n minus layer, and next n plus and this n plus layer is again diffused into the n plus layer, and next this is SiO2 layer, and next there are metals, and next these are the source, gate and silicon. So now here this is regarding construction. So this is G gate, and next this one is n plus, and next here this is P, and this is n minus, and this one is a n plus. So now here if you see this one, so now here this is SiO2 layer, this is the body layer, P layer is the body layer, and n minus layer is a drift layer. So now here this last layer is a metal layer. So here it is a vertically oriented structure. Vertically oriented structure always maximizes the cross-sectional area. That cross-sectional area increases the current rating. So vertical oriented structure increases the current rating, and this n minus layer increases the breakdown voltage of the device. So now here n minus layer breakdown voltage depending upon this width. So that already we discussed in the power BJT and power diode. So now here in this the working. So first here VDD 0. So how it will works, first I will explain. So now when VGS is positive with respect to, this is VG is positive with respect to source. So now here what will happen, there may be a channel. So there may be a channel will be created, electric field will be generated here. So initially when you apply VDD, when you apply drain is positive with respect to the source. So this is minus. So this is in forward bias. This is in this is in reverse bias. This is in reverse bias. So here there is no possibility to current flow here. So now here what will happen? Here there is a reverse bias. There is no channel to current flows from here to here, from drain to the source. So now here if you give the positive supply to the gate, and there may be an electric field will be generated here. So now there is a channel. One channel is created. N channel is created in the P region. So now here from drain to the source current will flow. So how it will flow? So first electrons flows from N plus to N plus region to N channel, induced N channel of P region. After that N minus layer, that is drift layer. Next N plus layer to the drain, source to N plus layer, and this induced N channel, this of P region, and this N minus layer, and next N plus layer and drain. So now electrons flows in this direction. Now current will flows opposite to the electrons direction. Same way for this. So second MOSFET, basic MOSFET. So now here in this way. So now here this current conduction due to the electrons only, not holes. There is no holes concept, only electrons. This the power MOSFET, electrons due to the electrons only current conduction is possible. So because of this reason, it is a unipolar device and it is a minority carrier device. There are no holes, only majority of the carriers are here, only electrons. So now here another thing is here. First, initially, if you apply VDD, VD is positive with respect to the this source. There is a reverse bias, no current flows, and when you apply positive supply to gate and negative supply to the source, and there may be a channel will be induced electrons flows from source N plus and induced N channel of P region N minus and N plus and drain. And now here current flows from drain to the source. So now in this way power MOSFET will works. And here what will happen? So here you can see, if you observe one thing here, this is N plus. This is N plus and this is N minus, this is P. So N plus, N minus and this is P. So now here N plus N minus P means this is parasitic MOSFET. So parasitic MOSFET means this is N plus is the emitter, N minus is the collector and this P region is the base. So now here what will happen? So now here this is parasitic MOSFET. So now here this is emitter and this one is the base. This is the base. So now here this is the metal. This is the metal. So metal short circuits this emitter and base. So this short circuit emitter and base means here. So what will happen? It short circuit means the voltage between emitter and base is 0. So now it is in cutoff mode. So there may be possible to parasitic BJT, but here because of this source metal short circuits emitter and base, and next that voltage is 0 in between base and emitter, and next base and emitter is 0, this is collector, and next because of that reason it is in cutoff mode. And another thing is it is a one parasitic diode will be exist. So this is anode and this is the cathode. So current flows from source to drain. So observe carefully here. Actually current flows from drain to source initially, but here inbuilt diode, this inbuilt diode, because of this inbuilt diode current flows from source to the drain. This is inbuilt. So actually this is the power MOSFET diagram. So now here drain, source, gate. So now here this is inbuilt diode. So because of this reason it is a bidirectional device. Bidirectional devices are used in the full bridge, half bridge and full bridge converters. Now here converters. So now here next transfer characteristics. What are the transfer characteristics? Transfer characteristics are drawn between this ID, this is drain, this is source, and this one is a gate, and this is ID cross, and this VDS, this voltage is VDS. So if you draw the graph between ID and VDS, and then here it will take some time to charge. So this is this voltage is VGST. So to charge threshold value, to charge this gate source junction. So that voltage is VGST, and after that it will looks like this. These are the transfer characteristics of power MOSFET. and after that output characteristics of power MOSFET are here, same diagram. So drain, source, gate, and if you draw the graph between ID versus VDS, in the previous one IGS I think, ID versus VGS, sorry, VGS, and next here ID, here ID. So now here this initially this voltage is VGS1 around 1 volt, and after that increase the this VGS values, and next increase, and next this ID increases and constant, and next breakdown. So now it looks like this. So now here this is a cutoff mode, this is the ohmic region, cutoff region, ohmic region, and this one is the active region. So these are the output characteristics. And next here switching characteristics are most important. So power MOSFET is used as a switch. So either switch, what do you mean by switching character? Either switching characteristic switch, it acts as a switch. So turn on and turn off analysis must be here. We must study this analysis. So now here if you give the supply, gate supply, if you give the gate supply, and next here this is the supply voltage VGS, and now here there are two characteristics, one is turn on and second one is the turn off. In the turn on characteristics, if you give the supply, so what will happen? So during, so here there are two times, TDN, so turn on delay time, and turn on rise time. So TDN and rise time. So what do you mean by rise time? Means during which input capacitance charges to VGST. So during which input capacitances rises to VGST here. VGST. So input capacitance rises to VGST. So now this point. So now here after that rise time means here during which so gate voltage rises to VGSP, from this VGST to VGSP. So VGST to VGSP. So this period is the TR, or in another way we can define this. This VGSP means here VGS means a sufficient voltage to drive the MOSFET into the on state, due to the on state. And ID, another definition in another way we can define this one. ID rises to, increases to from 0 to full ID, next maximum value of this ID. So this is TD and TR. So TD plus TR, TND, so TDN plus TR is known as a turn on time. And next, what about turn off characteristics? Turn off characteristics means here it is represented with TQ. So TD plus TF. TDF means, TDN means turn on delay time, and TDF means turn off delay time. TF means fall time. So now here TDF means here during which input capacitance discharges to gate position. Now this voltage. So input capacitance discharges to gate drive voltage to VGSP. So this voltage to VGSP. And next here, what about this fall time? This fall time, that is TDEF, and this fall time during which input capacitance discharges to from VGSP to VGST. And another way we can define from the ID to, from the ID to 0. So this is fall time. So fall time plus this turn off delay time summation is turn off time. So this turn off time is always less than this circuit turn off time. Circuit turn off time is greater than this device turn off time. So these are the switching characteristics And next, what about advantages? What are the advantages? It is a majority carrier device. This mainly conduction because of electrons only. Majority of charge carriers are electrons. It has positive temperature coefficient. Therefore, it is easiest device to parallel. Next, here it has very simple gate drive and less cost, and gate has full control over the operation, means it is a fully controlled device. Already I explained, it does not require any commutation circuit. And next, it can operate at high switching frequency. So it is a majority carrier device. It is a unipolar device, means only electrons, there are no holes. So now here turn off time is very less. Turn off time is very less means here during turn off no need to remove the holes concept. So that will take time. So here turn off time is very less. So time is less means here that frequency is very high. So it can be used for high frequency, high switching applications, that is up to 100 kilohertz. And next, it has short turn on and turn off time. So because of less number of holes means here, and it does not require any commutation circuit. So it has full control over the operation. So now here it is free from the secondary breakdown because it is a positive temperature coefficient. It has small size and less expensive. And next, it is a fast switching speed. So now these are advantages. Now coming to the disadvantages, every device has its own advantages and disadvantages. See the disadvantages. First, conduction losses and on-state losses are very high. Because of drain to the source, there may large amount of resistance that creates the on-state losses, and suitably only for low power applications. If power dissipation is more, means it can be suitable only for low power applications. And next, here it suffers from static charges, and it has asymmetric blocking capability. And next, what about the applications? So these are the applications. It can be used in the uninterrupted power supply UPS, relays, SMPS, switching mode power supply, and high frequency base drives, power amplifiers, and next, display drives. Now, the final conclusion is the difference between power BJT and power MOSFET. So now here power BJT structure, here I am drawing PNP. So now here NPN. So now this is emitter, base. This is base. This is emitter, and this one is the collector. Here I am drawing drain, source, and this is the gate. So now here emitter, base, collector are the three terminals, and here also drain, source, gate are the three terminals. And it is a minority carrier device, it is a majority carrier device, and next, it is a bipolar device, it is a unipolar device. Already we discussed all these topics. Just I am giving the final conclusions about BJT and power MOSFET. And it is a controlled by base, and it is controlled by gate voltage, gate base current here, base gate voltage here. Because of that reason, it is a current control device, and it is a voltage control device. So driving circuit is complex and costly, and driving circuit is very simple and less costly, and switching losses are very low and switching losses are very high. So this is most important. IGBT, power BJT advantages, switching losses are very low, but only the drawback is power MOSFET is switching losses are very high. So conduction losses are very high, and here conduction losses are very low. Turn on and turn off times are very high in case of power BJT, and turn on and turn off times are very short. Now here the switching frequency is very low, 10 kilohertz, and here the switching frequency is very high, that is 100 kilohertz. So now here it has negative temperature coefficient, it has positive temperature coefficient, and power BJT, paralleling of power BJT is very difficult, but here it is very simple in case of power BJT, power paralleling, and Power BJT suffers from the secondary breakdown, and power MOSFET free from the secondary breakdown. There is no secondary breakdown. Thermal runaway is possible, and here there is no thermal away. And next, it can be suitable for high power applications because low power dissipation. Here it can be suitable for low power application because large amount of power dissipated across the drain and source, and the voltage and current rating are 1200 volts and 800 amp, and here the voltage and current ratings for power MOSFET 500 volts and 140 amperes. And what are the applications of power BJT? Here we can be used in inverters and SMPS and AC motor control. But here power BJT we will use this UPS, SMPS, static VAR, voltage ampere reactive, and AC motor control. And next, it has low input impedance and it has high input impedance, and it has high input current, it has low input current, and its safe operating area in first quadrant, and its safe operating area in first and fourth quadrants. So this is regarding power BJT and power MOSFET. So I hope this power MOSFET concept, this diagram, circuit symbol basics, construction, working, transfer characteristics and output characteristics, switching characteristics, and next this advantages, disadvantages and applications. These are I hope all these are very clear to you. Thank you very much to you all.
Like, share and subscribe. Hit the bell icon for more updates.